Well, welcome back, and this is the very last of the content for our option for MedChem. And we've just got to look at a little bit of the environmental impact of some of the synthesis of medications, what that means, and the considerations that we need to make in terms of how chemicals are disposed of, or perhaps the safer way to synthesize some chemicals. We'll also touch a little bit on nuclear waste. This is relevant to a HL topic, but you do need to know about the waste aspects of nuclear chemistry in SL. So let's start taking a look at what we need to know. So the assessment points for this include an understanding of what high-level waste is in terms of nuclear radiation. So it's the amount of ionizing radiation and how long it lasts, in contrast to low-level waste, and we'll look at examples of both of these kinds of waste. The problems associated with antibiotic resistance, which we have already touched on during talking about bacterials, antibacterials and things like that when we talked about penicillin, and if you do biology you will have talked about a lot as well. We need to be able to describe the environmental impact of medical nuclear waste disposal and the discussion of environmental issues related to leftover solvents. Okay, so solvents being the things that we run our reactions in. Now that you've done some of your IAs, you will have seen perhaps some more solvents, things like dichloromethane, propanol, water is a solvent, of course, hexane or light petroleum spirit, those kinds of things. There's different kinds of solvents that we need to use for different synthetic applications, and when we are using these for the synthesis of drugs, we then need to look at how we can dispose of those properly after they've been collected, because we can't just put them down the drain. You need to be able to explain the dangers of antibiotic waste from improper drug disposal in animal waste. So this is linking back to the understanding of antibiotic resistance, but then being able to explain that in terms of how it arises and the different concerns that we have with it. You need to be able to discuss, so remembering discuss means to talk about the benefits and explain those in terms of the benefits and perhaps limitations of green chemistry, which is a sustainable chemistry approach, which we'll talk about, and I have uploaded some handouts about as well. And then you also need to be able to explain how green chemistry was used to develop a precursor for Tamiflu, one of the anti-influenza drugs that we looked at. Okay, so that will be our case study for talking about green chem in terms of this option. So while we make things, as we've discovered by discussing equilibrium and learning about equilibrium, very few things actually go to 100% yield. Okay, and we've looked at the side effects that different substances can elicit on our bodies. So if we're making things in the pharmaceutical industry, we need to also be very aware of the waste products that we are generating and the waste that we're generating and how they're disposed of, because they can have significant environmental impact. So this can be excess pharmaceuticals, it can be nuclear waste from the generation of radioisotopes for the treatment of cancer, it can be solvent waste from just synthesizing our compounds in general. So solvent waste we have dealt with a little bit in our own laboratories, where we collect organic waste and we don't put it down the sink. But essentially the complex structures that we use for in drugs require us to use a wide range of different solvents to extract or to solvate a reaction so that the reactants can collide effectively. Most of these solvents are organic in nature, so they're made from organic compounds, and they can often have high toxicities or carcinogenic properties. So we can't just dispose of them willy-nilly. They need to be considered and disposed of properly. This can be through chemical treatment, so it can be treated chemically to change it into a different compound that's less toxic, or unfortunately in a lot of cases they burn them off, which can release toxins into the atmosphere. So solvent waste is one of the largest contributors to the waste facing pharmaceutical companies, and it needs to be collected and paid to be disposed of. Sometimes it's buried or just stored in large bunkers. Recently there was a fire, you may have heard about it, in North Melbourne, north in the Melbourne northern suburbs, where a chemical storage facility was set on alight, and that was a very dangerous fire. So because of the nature of these chemicals, they need to be treated quite carefully, and there's a lot of regulations around these. So one of the things we can do as chemists is to try and address our solvent concerns by using safer or less toxic solvents where possible. So we need to address the solvent suitability against 3 criteria. So one is the toxicity for workers. So is it carcinogenic, i.e. causing cancer or other health issues, or does it have a direct toxicity, i.e. is it poisonous? Does it directly cause a toxic response in the person? The other things that we need to consider are things like flammability, explosiveness, or the production of toxic byproducts. So if we think about all the alcohol solvents or most of our hexanes or things like that, they're fuels, so they have high flammability. Their volatility needs to be considered, and boiling points for safe use in the laboratory, and whether or not they can form explosive peroxides or form explosive compounds themselves. The last one that we need to think of, so we've got toxicity to people using it, we've got the process safety, is it safe to use in the process that we want, and the third one, of course, is harm to the environment. Will it cause contamination of soil or waterways? Does it contribute to ozone depletion, so chlorofluorocarbons that were used a lot in the 80s but have been severely restricted in the following decades? Or does it form greenhouse gas or other emissions that contribute to air pollution and acidification? So the preferred solvents, of course, are ones that are going to have less environmental impact and are safe for us to use. These are things like water, ethanol, propanol, well, 2-propanol in particular, propanone or ethyl ethanoate. These ones are safer for us to use. They don't have a lot of long-term toxicity, and they don't contain compounds like the halogens, like chlorine and things like that, which can be particularly bad. So we consider these alcohols and water to be much more desired in terms of designing a synthesis. Our undesirable ones are dichloromethane. A few of you were looking at some projects in your IAs looking at dichloromethane, and we're encouraged to move away from that, and that's because it has associations with toxicity. It's highly volatile, needs to be used in a fume hood, and other safety concerns. Methanol is also not good. Tetrachloromethane is a chloro-based compound, and typically chlorine-based compounds are very dangerous. Diethyl ether, this is largely because diethyl ether's boiling point is about 30 degrees or 29 degrees. They used to use this as an anesthetic, and if any of you have had the green whistle, if you've broken a bone or had to travel in the ambulance because you've dislocated something, they may have given you a green whistle, and that contains an opiate plus diethyl ether. That quite pungent smell it has, and that diethyl ether is essentially an anesthetic. So it can be unsafe to work with. Benzene, which is incredibly toxic and used to be used widely, but its use has certainly decreased in labs now. So I've made reference to green chemistry. The overriding principle of green chemistry is a thing we call benign by design, and benign means non-harmful. There are 12 principles, and I encourage you to look at the couple of links that I've put up, which go through these in more detail. They're basically 12 principles aimed at reducing a number of different harmful aspects of chemical synthesis and processes. These are not all designed to be environmentally friendly. It's not an environmentally driven sort of idea or process. It's driven to reduce the use of harmful solvents, increase yields, and things like that. So let's have a look at them. Number one is to prevent waste, so using synthetic pathways that generate less waste or less byproducts. atom economy, which is linked to waste. So atom economy basically is a percentage, and there is an equation given for it in your data booklet. It's the percentage of the reactants that end up in the final products, and I'll do another video going through that in a little bit more detail. Less hazardous synthesis, so reducing pressure, reducing use of dangerous chemicals, those kinds of things. Design benign chemicals, so these are chemicals that are non-harmful to start with. Benign solvents and auxiliaries, so chiral auxiliaries and other things that we use to help us make the compounds that we want, making sure that they are also non-dangerous and non-toxic. Energy efficiency, so not wastefully using energy where we can avoid it. Renewable feedstocks, so this is talking about our reactants coming from renewable sources, so the use of vegetable oils for biodiesel, or the use of SO2 from power plants in order to produce sulfuric acid. Those kinds of things, using waste products that are made from other industrial processes or things that we can easily renew as our reactants. The reduction of derivatives, which is sort of looking at the number of compounds that we make. Using catalysts to reduce the stoichiometric load. So sometimes when we do a synthesis, we'll run things in a 3:1 ratio, even if the reaction is a 1:1. So we boost up the stoichiometric proportion of 1 in order to try and push the equilibrium. So using catalysts as well to increase our production of a certain chemical. Designing for degradation, so making biodegradable or degradable compounds. Real-time analysis for pollution prevention, so being able to monitor the products that we are, or the byproducts that we're making during a synthesis, to know what's happening in terms of pollution. And then inherently benign chemistry for accident prevention. So generally things that are just safer to do and to use in order to increase A, the safety of the workers, B, the quality of the environment, so less degrading to our environment. So the pharmaceutical industry over the last decade or so has been, or even more, has been looking at trying to improve its green chemistry approach. So you don't need to know examples of these, but we do need to know the one case study which we're going to look at. So essentially many of these have improved the atom economy. So if we look at the synthesis of ibuprofen through the semi-synthetic pathway, it is a 3-step process with an atom economy of greater than 70%. So over 70% of what we put into the flask is coming out in our product. The original pathway, before it went through review and redesign, used to only have about a 40% atom economy. So 60% of the atomic mass that we were putting into the reaction flask was never being used in the production of the product. So you can see that's a much less efficient way to do this. Viagra is also produced with drastically reduced waste, and it continues to be an area of research focus on how to improve synthetic pathways, improving the green chemistry approach. It's not just an altruistic thing for industry. The disposal of things like chlorinated solvents and the use of energy and things are all costly. So if they can take this more benign by design, not only is it more sustainable and better for environment and ourselves, it also reduces their costs. Okay, I'm going to stop this video here, and then I'll do a second video on nuclear waste. See you then.